Hi, everybody. So I'd like to talk about grammars and automata because some students have been asking about deterministic pushdown automata, and I just thought let's make a little lecture video to clarify some concepts and then hopefully see where we're going with that. So there'll be more information probably than your question actually requested, but automata are thought of as recognizers of strings. They accept or reject. We have talked about Turing machines, which also have this ability to say what's on the tape. Grammars are more like generators of strings. We start with a start variable, we choose a rule to apply, and then we just keep taking variables and then replacing them in place with whatever string it makes sense to replace it with. And we'll stop when there are no more variables. Now, grammars, because they have this kind of text-based notation, they're pretty easy to work with, and you can build a parser from a grammar, which is pretty useful when you're building compilers. Now, there is this concept of ambiguity, which we don't really like when we're building compilers because it makes the compiler hard to build, but there are sometimes ways to generate strings in multiple ways. It's similar to how a PDA can accept a string via different paths, but they're not exactly the same concept. Now, if all you care about is whether the string is in the language, then it doesn't matter. When we use the grammar to generate a parse tree, we might care about which possible parse trees we get. And the classic example is, of course, if then else. You have multiple ways to parse this particular input. I could think about that if else on the inside, or what if it was an if with an if on the inside and then an else, right? There are multiple ways to do this. We had a homework problem on this as well. Now, since there are two valid parses for this input, then this grammar is ambiguous. Okay, so this is the concept of ambiguity, which means that there are two ways to validly parse this input given the grammar using a leftmost derivation. All right, so if there is only one leftmost derivation, then it would not be ambiguous. Okay, so here's a particular parse. I can take the statement, take an if, replace it with an if then else, and then replace that statement with an if I like. Okay, and that's because there's two ifs here. Another way to parse it would be to do if then, and then replace that then with the if statement. So that gives me, again, this concept of ambiguity. The grammar is ambiguous. So let's just make sure we understand this definition. A grammar is ambiguous if there is an input string for which there are two or more valid parse trees, or the other way to think about it is two leftmost derivations. Now, yeah, okay, so we have to be a little bit weird here, but you can do different derivations because I could have a leftmost and rightmost derivation and they don't have to be the same, but it will be true that the leftmost derivation will be the same or all rightmost derivations will be the same, okay? Maybe another way to do it if you're more visual is to draw the parse tree for it, which will be the same regardless of the derivation order. Okay, so that is the definition of ambiguity. Now, ambiguity does not affect the language. A grammar just produces a set of strings, so as long as you can get there in some way, then you're good to go, right? It is in the language. And the ambiguous grammar can produce strings in more than one way. It's kind of like having multiple paths through an automaton, each of which leads to an accept state. And ambiguity produces multiple parse trees, which means multiple interpretations or meanings. What else and if go together? This can cause actual problems because the programmer thinks it should go one way and the compiler thinks the other one. And this can lead to bugs. In your best case, it crashes, but if it compiles properly, then you might be in trouble. So in practice, we often care about which parse tree was produced by a parser. We want it to be unambiguous to reduce confusion for the human. Now that I've talked about ambiguity, I want to talk about deterministic PDAs. Deterministic PDAs are not the same thing as ambiguous grammars. There are grammars which are unambiguous, but yet the pushdown automata for it has to be non-deterministic. Okay, so let's take a look here. A pushdown automata, by its nature, is just going to be considered non-deterministic. That's the default. Um, to have a deterministic pushdown automata, you would say, look, the next transition of the deterministic pushdown automata is completely determined by the next input symbol and the top stack symbol. In other words, you can take only one path. If you apply this restriction, it actually prevents you from accepting some things that are considered context-free. So there is a concept of a deterministic context-free language, which is the language that's accepted by a deterministic pushdown automata. And unlike with NFAs and DFAs, where they were actually the same, or even non-deterministic and deterministic Turing machines, they are not the same. This is the one weird sort of case. So let's take a look at PAL even, right? So this one, if you write the grammar, it's actually not ambiguous, but we have to kind of guess where we are in the middle of the string, right? So I don't know when we have hit W and we start to need to look at W reverse. And so basically we create this epsilon transition going between 2 and 3 that says like, okay, let's just push a bunch of stuff onto the stack. At some point, guess that we're in the center and then start popping. And then if we matched it, then we're good. It is an even palindrome. So this pushdown automata is non-deterministic. That epsilon arrow from 2 to 3 is necessary. And so you can do it a lot of ways badly, right? Like, oh, I'll just push 1 and then go to epsilon. Oh, I failed. It doesn't matter, right? Because there is one, if the string is good, for it to work. Let's compare it to balance, which is A to the n, B to the n. And notice here, this is also easy to draw as a non-deterministic PDA, but it is possible to say, okay, I'm done reading the A's. So once I see a B, I know to start counting them. And yeah, I have this kind of like careful bookkeeping of making sure if I pop this A off the stack when I read this B going from 2 to 3, that I might be off by 1. But otherwise, like it's easy to see I got to the B's. Like we're good, you know? So this one is considered a deterministic PDA. I actually think it's easier to draw as non-deterministic because you just count all the A's and then count all the B's separately in two different sort of streams. But it's not so bad to convert it to one that is deterministic. And what you can see here is that there's only one transition at every stage. So at 2, like either the top symbol, the symbol that you're reading is an A, or the symbol that you're reading is a B. And then for 3, the only thing it can read is B's. It is okay to have epsilon transitions here because the point is that there's only one thing you can do from 1 to 2. And then from 3 to 4, it has to be that top symbol is a $sign. So the epsilon arrow from 1 to 2 is allowed because there's literally no other choices. So with the deterministic pushdown automata, weirdly, like you can have an epsilon arrow as long as the only thing that you could actually do. More formally, you would say there's only one move that the pushdown automata can make. So we remember our delta transition, and we would say it's the states Q cross sigma union epsilon cross gamma union epsilon, and that takes me to Q cross gamma union epsilon union the empty set. And then now you can think about it in terms of these 4 cases, which are if you have a Q in the state states A, which is in the input alphabet, and X, which is in the stack alphabet, then exactly one of these 4 things is not empty set. Delta QAX, right? So it has both a pop and a push. Delta QA epsilon, all right, and then delta Q epsilon X. So either a pop or a push, or delta Q epsilon epsilon. So we need exactly one of those to be good. The typical operation here is to consume an input symbol, match, and pop stack symbol. For that first one. For the second one, we have no pop. We don't care what's on top of the stack, but it's important that we have that input symbol. And then for the third one, delta Q and then epsilon X, we don't consume an input, but we need to make sure that we're matching the top of the stack. And then finally, we could have don't consume input, but we don't care what's on top of the stack. But it's the only one that's available. So you can have an epsilon transition here. Okay. So hopefully, just for your sake, what I would do is write down these 4 states or these 4 conditions and say only one of these can be true. That is how I'm going to tell if it's a deterministic pushdown automata. I have here an example of a deterministic context-free language. It's just like the palindrome, but it's marked. So what I've put here is like a special symbol C that is going to be a palindrome with C exactly in the center. And now let's think about drawing a pushdown automata for this language. So I know that you know how to do this based on the previous example that I had, which was WWR, right, which was a non-deterministic PDA. You would just grab that image and then change it to apply that C transition, and all of a sudden it's deterministic. Okay, so yeah, we're like good to go. And again, the epsilon transition arrow from 1 to 2 is allowed because there are no other transition choices. It's only one of the 4. There are some deterministic pushdown automata limitations compared to pushdown automata. So, for example, palindrome, we can't recognize that. We also can't recognize odd palindromes. Another fun one is A to the I, B to the J, C to the K, where either I is equal to J or I is equal to K. You know that you could do A to the I, B to the J, right? Because that's the same language that we've seen before with A to the N, B to the N. And we can do B to the J, C to the K, where in the case where I is equal to K. But it turns out you'd have to make a guess at the beginning as to which one of those 2 things it's going to be. Proving this, like actually showing that it's not deterministic, would require a bit more machinery than we have in 333. So you know that you can draw a pushdown automata for it. Actually proving that there is no deterministic one requires a little bit more. But it would be good for you to draw a pushdown automata for this language A and see why it's deterministic and compare it to those 4 conditions that I said only one of those transitions can be true. So what you need to know is not the formal definition, but the meaning, right? And you should be able to draw in the Chomsky hierarchy the set of deterministic context-free languages, which would be under context-free languages in the Chomsky hierarchy. It includes regular languages, but not all of the context-free languages. The set of context-free languages is strictly larger than the set of deterministic context-free languages. And then finally, if I gave you a pushdown automata, you should be able to identify whether it's deterministic or non-deterministic, which is just PDA. All right, our last couple of topics that we have in context-free languages, now that it's a little bit of review based on where this sits in the, when you're watching this, basically. But pushdown automata and context-free languages are equivalent. We've gone over why that's the case. And then there are languages that are not context-free. So there's context-sensitive, which we don't really talk much about. I just want you to know they exist. And then we will be talking a lot about recursively enumerable languages and Turing machines. Context-free languages will be important in some things that we say about decidable languages with Turing machines, which we'll see a little bit of later. And of course, we'll talk about the pumping lemma for context-free languages. We have, you may have already seen that video. If not, you should go and watch it. So yeah, these are the things that we are going to have. We end with Turing machines as the final kind of top of our Chomsky hierarchy and talk about undecidability before we move on to complexity, which will be P versus NP. Again, all this kind of depends on when you are watching this, but I hope that this lecture video sort of clarified the difference between ambiguity in grammars versus deterministic pushdown automata. That's all I have. Thank you for watching.